Welcome to this lecture of calculus. In this lecture, we shall study the proof of the intermediate value theorem. This theorem states that a continuous function assumes every value between its bounds. Before taking the proof of this intermediate value theorem, we shall first learn about what we have in the location of roots theorem. The location of roots theorem states that if f of x is a continuous function defined on the closed interval a b such that f of a and f of b are opposite in sign, then there exists a root of f of x in the open interval a comma b. So the location of roots theorem therefore states that if a continuous function is defined on a closed interval a b and f of a and f of b are opposite in sign, this means that either f of a is positive and f of b is negative, or f of a is negative and f of b is positive. Then there is at least one value of x in the open interval a b at which f of x is equal to 0. Now let's first try to understand the location of roots theorem. Graphically, we will not take up its proof. Now here we shall just construct a graph that has this kind of a situation. So suppose we have a point A here and suppose we have a point B here. Now this theorem states that the functional values f of A and f of B are opposite in sign. Let's first take the situation that f of A is greater than 0 and suppose f of b is less than 0. Now this f of a greater than 0 means, so this f of a lies above here, above the x-axis, and f of b less than 0 means f of b lies below the x-axis. So therefore this point has the coordinates a comma f of a, and similarly this point here has the coordinates b comma f of b. Now since the function is continuous from a to b, so therefore wherever the graph goes between a and b, it finally will reach this point f of b here. So therefore, in order to reach this point f of b from f of a, the graph of the function f of x has to cross x-axis. So therefore, suppose if the function f of x behaves like this and reaches f of b in this way, then this is the point at which the functional value is equal to 0. And similarly, we can have the graph like this. So suppose first it goes up, then it crosses the axis, then it again goes up, and then again crosses the axis. So now here in this situation, these are the values. Suppose this is c1, and similarly this is c2, this is c3. So in this case, the function will have three different roots between the interval a to b. So this is the case when f of a was positive and f of b is negative. Now similarly, we can have the case that f of a is negative and f of b is positive. So now let's consider a case that f of a is less than 0 and f of b is greater than 0. Then if this is the point a on the x-axis, and then suppose f of a is a point here, and suppose this is a point b on the x-axis, and suppose f of b is here. So this point has the coordinates b comma f of b, and this point has the coordinates a comma f of b. Then as the graph of the function is continuous, therefore it starts at this point a comma f of a and it has to reach the point b comma f of b. So therefore the only way to reach b comma f of b is that the graph of the function must cross the x-axis. So therefore the graph of the function may be like this. So then this will be the point c at which the functional value of f of x is equal to 0. Now using this theorem we will try to prove the intermediate value theorem. Now before proving, we shall again take the statement of the intermediate value theorem. So this is the intermediate value theorem. So therefore this theorem states that if we have a function f defined on the closed interval a b, then we first compute the values f of a and f of b. In case any real number that lies between f of a and f of b, then there is at least one point c belongs to the open interval a b, that for which f of c is equal to k. Now let's take the proof of this theorem. So first consider a function. Consider a function f defined from a closed interval a b into the set of real numbers, which is continuous, Then we know that a continuous function defined on a closed interval must be bounded. Then by boundedness theorem, f of x is bounded. Therefore, f of a and f of b are both finite. So therefore, both f of a and f of b are finite numbers. Now we have suppose a real number k belongs to R such that this f of A is less than K is less than f of B. Now at this stage we shall keep in mind that we can also have the situation like this: f of B is less than K is less than f of B. So if we have this kind of a situation, then we will have exactly the similar proof that we will take in the situation f of B less than K less than f of B. Now here, in order to prove that we have a point C belonging to the open interval AB that takes the value K, for that thing we will define a new function. So now define a function g of x which is equal to f of x minus k. Then since f of x is continuous and k is a finite real number, therefore the function g of x is continuous. So clearly g of x is continuous and in fact bounded also, and bounded on the closed interval a comma b. Now let's compute the values g of a and g of b. Now here this g of a, this is equal to f of a minus k. But now if we look at this equation, f of a is less than k is less than f of b, from this equation we can clearly see that f of a minus k, this will be less than 0. This is less than 0 because f of a is less than k. Similarly, let's consider this g of b. Now this g of b is equal to f of b minus k. This is greater than 0 because from this above equation we have f of b is greater than k. Therefore, in this case, f of b minus k is greater than 0. So therefore, what we have, therefore, g of a and g of b have opposite signs. Therefore, g of a and g of b have opposite signs. Hence, by location of roots theorem, there exists a point C in the open interval a comma b such that g of c is equal to 0. But the function g of x is defined as f of x minus k, so this implies f of c minus k is equal to 0, so this implies f of c is equal to k. So this completes the proof of the intermediate value theorem. Now let's consider one example where we will use the intermediate value theorem to show that a given function or a polynomial has a root in a given interval. Consider a function f of x is equal to x cubed plus 2x minus 1 defined on the interval 0, 1. Then let's compute the values f of 0 and f of 1. Then f of 0 is equal to minus 1 and f of 1 is equal to 2. So then by intermediate value theorem, which is IVT, for every k belonging to R with like this minus 1 less than k less than 2, there exists a point C belonging to the open interval 0, 1 such that f of C is equal to k. Now in particular, if k is equal to 0, then minus 1 is less than 0 is less than 2, so there exists C belonging to the open interval 0, 1 such that f of C is equal to 0. That means this polynomial x cubed plus 2x minus 1 has at least one root in the open interval 0, 1. So this is an application of the intermediate value theorem.